there is the whole list of exponent rules that I'm sure you could just walk through yourself. This is a nice little table that reviews each of those. So I thought I'd give you an example, just a couple of reminders of the hiccups that we're all accustomed to, things that get easily mixed up. If you guys do product of powers, this is the idea in that first example at the top. When you have the same bases, we call these. So remember, if you talk about exponents, we talk about their base and we talk about their exponent. The base being a and the exponent being m and n, respectively, in these two in this example. When you multiply same bases, you add their exponents. And I'm sure that all comes to mind when you think of like x to the third. If I take it times x to the fifth, that will make x to the eighth, for example. That's what we've dealt with for a while now. We just got done with polynomials and dealing with that rule. Now, then, seemingly, I think in a sensical way, if you do a base a to the m over a to the n, and I'm sure those sound the same in this recording, but when you're dividing with the same base, and you can subtract the exponents. You can write it as the cool thing is these exponent rules take two or more bases of the same kind, and it combines them into a singular base. And so it's a way of simplifying. It's putting them together. So we're dividing a to the m over a to the n, two exponential expressions, and what we get is one exponential expression when we're done. When you divide them, you subtract the exponents. When you multiply them, you add the exponents. Seems like multiplication and addition go together in exponents, and they do. And then division and subtraction go together when it comes to exponents, and they do. And that's a nice sensical rule. We all like this one, I think. This subtraction rule, I tend to think of it a little bit differently later, so I'm going to introduce that to you. But if I do x to the eighth over x to the third, to kind of parallel the one we just did, I would write that as x to the 8 minus 3, and that makes x to the fifth. Now, later on, I'm going to do what I call exponent battle, because I like to think of this as when you have the same bases, I like to look at their exponents and say, ooh, who would win between x to the eighth and x to the third? Well, obviously x to the eighth would, and by how much? Well, it wins by 5. And so, to me, what I think of is you write x to the fifth on top, where the winner is. I do this battle thing where I say who wins and by how much, and you put the winner, x to the fifth, or the amount that it won by, x to the fifth, goes on top where the most powerful exponential expression was. And so this will come in handy when we get to some other more complicated ones down the road. I like to think of it exponent battle. I'll explain that more later. But at the heart of it is, when you do x to the eighth over x to the third, it is a singular x to the fifth power when you're all done. To the power of a power, if you take an exponential expression and raise it to another exponent, then you multiply those powers. So we see that here. So if I have x to the eighth, and then I raise it to the fifth power, and if I can do multiplication, then it's x to the 40th. Okay, so 5 times 8 is 40, I hope. The next one is same idea, except what if I have within this expression here on the inside, I'm multiplying a times b, and I'm raising it to a singular nth power. You distribute that power. Now this is the one where we're going to get goofed up. So I can do x to the third, and this is, whoops, I'm stepping ahead of myself. If I do x to the times z inside here, and I raise it to the third power, then I can distribute that power to each of those, x to the third times z to the third. This is not to be confused with the following. This is the big no-no, remember? If it's addition, you can't distribute the power. So just so you know, x plus z, and there's to the third power, do not distribute, don't you dare. Do not distribute the power when it's addition. Don't distribute. That's like the ultimate sin, I think, in at least our world of pre-calculus. Don't distribute over a plus or a minus sign. And that's huge because multiplication, we just got done distributing the power just fine, but it's because it's multiplication or division, by the way. So don't distribute over a plus or a minus, but you can distribute a power over multiplication and now addition. I'm looking at the example here with a over b. You can distribute the power if it's a quotient. If what's holding your components together is multiplication or division, you may distribute a power to each of those terms as long as it's multiplication or division, not subtraction or addition. And that's one of our big errors that you're going to encounter along the way. So I'm going to make this example real fast. X to the, that's just x over z again. We'll just use that as our start. Then it would be x to the third over z to the third. Okay. Now we're going to start combining rules. You guys remember, I'm sure from Algebra 2, where it gets tricky is that you start combining all these rules together and you're making decisions about which rule do I apply in which order. And quite frankly, there aren't many You don't really have to go in a particular order as long as you obey the rules as you move through one step to the next. This last one, the reciprocal rule with negative exponents. If you have a to the negative n, that equals 1 over a to the n. And on the flip side of that, quite literally, if I have 1 over a to the negative n, then you can write that as a to the positive n. I think of it as wherever this is currently located. If you have a negative exponent, it means you can move it to the other part of the fraction. So if it's in the numerator, move it to the denominator, but you have to remove that negative power once you move it. If it's in the denominator, then if you want to remove that negative exponent, then you'd have to move it to the numerator and remove that negative exponent. So it's the reciprocal rule. It moves whatever is being raised to a negative power to the other part of the fraction, and then you remove that negative exponent. Okay, that's old school news, right? So I'm going to try the next couple of rules here. Okay, new picture here. A to the 0. Anything to the 0 is 1 until you get to Calc 2. And then we have some funny variation on that. In the world of limit land and limits, we actually have some change of this. But for all practical purposes in the real world without limits, a to the 0, anything to the 0 power is 1. And talk to your Calc 2 friends about that. We're encountering it right now, and it's blowing their mind, and it's been a lot of fun. A to the 0 is 1. Hey, but what about pi? Does that work? Pi to the 0? Is that 1? Yeah, it's 1. So any number to the 0th power is 1. So simplify. There's a whole bunch of examples on here, but this is just to kind of point out the variations on this. I know there's a negative exponent in there, but you can kind of apply the rules in your own particular order. Here's one order. If I see same base of 4, and I see them being multiplied together, I'm thinking, oh, I can write it as a single 4, and just add the exponents. And what I mean is literally add them, so be careful on adding a negative, and it makes 4 to the 2nd power. Now that's one way to approach it. Somebody else says, so there's your tomato approach. Here's tomato over here. If you want, you can deal with that negative exponent first. You can say, oh, 4 to the negative 3rd, it's in the numerator, top of my fraction, if I think of it as a fraction. Can I just move it to the denominator? Can I just say, hey, 4 to the 5th over 4 to the 3rd? Yes, you totally could. And then could I do the, hey, same bases are being divided, could I subtract their exponents? Yeah, you sure can. So 4 to the 5 minus 3, and that would be 4 to the 2nd, so you get the same thing. So the approach, in order you take these rules, is not terribly important. It's just being very true to those rules. So how about number 2 here? Oh, common error. When you square this, are you squaring 3? Or are you squaring negative 3? The difference is, am I doing negative 3 times negative 3, which is positive 9, or am I doing 3 times 3 and then making it negative? That's negative 9. Well, you have to look at what's being squared. The power applies to whatever it's sitting next to, and it is only sitting next to the 3. So this is like negative, and we're squaring 3. That's another way to write it that might be more clear. But whenever your exponent is next to something, it only squares what it's next to. If it's next to a set of parentheses like this, it is squaring all the contents of those parentheses. So a power applies to whatever it's sitting next to. This one is negative 9 because it's 3 squared, and then you're applying the negative. It's actually order of operations taking place. You're doing the exponent, you're dealing with that before you do your multiplying by negative 1. The next one, I'm squaring whatever it's next to, which is the parenthetical statement. That means negative 3 times negative 3. We got nove for that one. There, number 4, what are we squaring? Everything in the parentheses. If you want to write it out, sometimes that kind of clarifies it. It's negative 2x times negative 2x. And if I go the long route, what I do is I'm taking these two together. Negative 2 is 4. X and x makes x squared, and we're home free. Now somebody says, well, could I just distribute the power? Could I do that because it's product? Yeah, you could. You could actually take this, distribute the 2 to that, distribute the 2 to that. So I'm squaring negative 2, which is 4. I'm squaring x. I'm sharing the power because it's whenever you have a power and there's a product inside, you can distribute it, but not if it's adding and subtracting. The last one, or number 5, you're taking to the 6th power, 1x to the 6th. Well, 1 inside there, really, it can just be written as x to the 6th. So this is just x to the 6th, and then you put the negative out front because only the x is being raised to a power of 6. The difference, which I wish the example was on here, can I give you a 5.5 example? You want to jot that in there real fast? What if I had negative x to the 6th? Do you remember that if you take a negative to an even power, you basically have three pairs of x's being multiplied together, negative x's being multiplied together, and each negative x pair is a positive x squared. And if you have three of those, x squared, x squared, x squared, that's all positive, it's going to be positive x to the sixth. The shortcut rule is if you take a negative number to an even power, you're going to get a positive result. If you take a negative number to an odd power, you'll get a negative result. This ends up being positive x to the sixth in example 5.5, a different example that I made up. Okay. Amazing improvisational skills, I know, but that's positive x to the sixth. If you go to number 6 on the end here, I can distribute a lot. There's a lot of things I can share with. 3, you can distribute a power amongst all multiplication and division with it in this expression. So long as it's not addition and subtraction holding it together, you can distribute the power. We got 4 squared, x squared. This is how well you can distribute that power too. All components in there are attached by multiplication or division, so they can all receive that power of 2. So that's 9, 16, x squared. We got it all in that one. Isn't that cool? Now, they're just getting layer upon layer thicker, more complicated. You're going to have lots of practice problems to kind of navigate through, but you have experts in the room who can help you through the rest of it. I'm going to ask that you guys do lesson B, the notes that are on there. I don't have them in front of me. I guess I could pull up a picture on here. But it's filling in tables and answering questions about exponential expressions. But lesson B, I want you to take on independently. Just do it. You can handle it. And then if you feel moved, also the practice B that goes with it. I'm going to grab those from Central Print. You guys can rock and roll. Okay, let's finish this up real fast. In a nice compound expression right here, this rational expression with all kinds of stuff going on, what you do is you line things up. Remember, you deal with numbers to numbers. There's a 4. And if I get another color here for something else, I'm going to deal with F's. You know, F's work with F's, numbers with numbers, D's to D's. F to the first over F to the negative 1. I'm going to make that F to the, because I'm dividing them, 1 minus a negative 1. Could I deal with this a different way? Yes. I could move the F to the negative 1 up top and make it F times F. Both, by the way, when you're done, this will be a squared. F to the second power. Then I deal with my D's. Got to deal with the D's, got to deal with the D. Go big D tonight, I hope, or today for the girls. It's all about the defense, right? There's the D, and it's 2 D's being multiplied. So I add the exponents, 5 plus 2. I'll let you do the addition on these. I imagine you can handle that. So 4f squared D to the 7th. Moving on. Next one. We get the G's. When they're kind of spread apart like that, you just do numbers to numbers. 6 times 4 is 24, I hope. Addition, multiplication, you know, those are not my strengths. And then G to the 6th. Okay, because I'm doing G's of the same base, I'm adding 5 and 1. And finalmente, number 9. We're going to look at this. I can distribute this power like crazy to anything being multiplied or divided. Well, I should say anything. It's all parts that are multiplied or divided need to receive that power of 3. We got 5 cubed. We got x cubed. We got y to the, oh dang it, I've already got a power on this one. Do you remember what you do? If there's already a power on that variable, you need to multiply those powers. Power of a power. So it's going to be negative 12. And then I got z here to the 0 times 3 because it's power of a power, which is z to the 0, also known as a big ol' 1. Okay, now some folks in here, and even some of those who are helping out today are going to say, you can't write an expression with negative exponents in there. Maybe that's true. I don't know. There's like a rule out there. There's like exponent jail you could get thrown in or something. This, y to the negative 12, would be needing, in some context, you got to move that such that it is no longer a negative exponent. That means you would need to move it to the denominator and call it y to the positive 12th. And then keep yourself out of jail. If for no other reason, just stay out of exponent jail, please. Take care, y'all. Send me some texts or emails if you need something.